AI in our research. So my research is in soil science. So where we look at the application of machine learning to solve the problems of soil. In this review, we use machine learning, a type of machine learning, to go through the papers that are published in soil science that use machine learning. And we can classify the papers according to several topics that people have used machine learning in soil science. In particular, machine learning is used in remote sensing and also in spectroscopy using infrared to analyze the soil. And people have been using machine learning to try different methods so we can get more accurate prediction of soils. But it also being used in detecting soil contamination, detecting crop yield, detecting soil carbon and water in the soil, and also erosion. So machine learning has been used quite a lot in soil science. And usually the procedure is what we call a peso transfer functions, or functions where we can predict the soil properties. So for example, we go out and take some soil samples and we analyze in the lab. And what we can analyze is usually limited. For example, the soil type or the texture of the soil. But what we want to know is something more complicated. For example, how the soil is storing water, how much water it can store for plants growth. So we use machine learning models to translate or to convert from the input of, for example, soil texture or soil type into amount of water that the soil can store. And we use that information into simulation models, computer simulation models, so that we can make a estimate, or we can predict how the soil is going to function in producing crops, or for biodiversity preservation, or for conservation, or for land use planning. But many of the machine learning is still what we call as a black box. What does it mean by black box? That means that we take the data, we process it, and then we use some predictors, and we use a black box model, a machine learning model, that we train the data, and then we get the results. So what do we mean by black box model? That means that it doesn't really need any basic knowledge or basic soil science knowledge to produce any meaningful outcomes. As a result, we have papers that try to use machine learning models to predict soil, what they call as soil classification, but it actually does not have any useful meaning for application in agriculture, or even application in engineering and so on. So for example, this paper say that they can make a classification based on soil samples to predict soil properties, soil class. But the soil class is in fact the texture class, which are very easily obtainable in the field. So this paper is actually quite useless, because you can actually make the predictions in the field and you don't even need to use machine learning. So what we need to do is that we need to solve soil science problem specific model. So this can be other disciplines, it can be geology, it can be engineering. That means that we need to have some inputs in the process of machine learning, whether to do with the data, to do with the variable selection, to represent the model with the knowledge of domain knowledge, and then to make some interpretation and applications which are related for our specific problem of soil science problem. So I'll show you some examples, and we've been working with the colleagues at Universitas of Andalas and Universitas of Mataram. And the first example is that we want to make maps of soil properties in the Lombok area. So first we collected some data from the observations in the field. And then at the same location, we collected remote sensing data. That could be data about elevation, about vegetation, about the wetness, and so on. and we intersect the observations with the remote sensing data. And by doing that, we get a prediction that we can build a model that is machine learning models that allow us to make a prediction of the soil properties at unseen location not being observed in the field. So, for example, this is an area. This is the Lombok where where Professor Bambang has collected observations in the paddy field area throughout Lombok. And what we have is we have remote sensing images and we have elevation information. By calibrating these observations with existing remote sensing data, with and then training a machine learning model, we can predict, for example, here the carbon content of the area, where we can observe that the areas where they have been heavily grown with cropping and paddy fields, we have reduced carbon content compared with areas where there's still forested vegetation. We also look at how to map the erosion risk, for example, in the Lombok Island. So here, the Lombok Island as well. So you see that this is the peak of the mountain, and then here is the flatland area, and then sorry, the flat area here, and then also some sloping area. So we want to map the erosions risk. So the factors, the topography factors that affected the erosion risk is the slope. So the slope is the length of the slope, and also the degree of the slope angle. So what we call as the LS factor. So in this, we calculated the LS factor. That means that if the slope is longer, then you have a higher risk of erosion. And also if the slope is steeper, you get a higher risk of erosion. But in order to, but the slope is just one factor, but the other factor is about the what is the coverage of the soil, or if the farmer keep tilling the soil, if the soil is always on fallow or bare, it doesn't have any cover, so it will have a higher risk of erosion. So we take the images, the satellite images from 2013 and 2024, and we look through the data where there's no cloud, and then we look at the indices where they are. So each location or each pixels on the picture where they have whether it's under vegetation or it's bare or there's no vegetation. So, and then we calculated what we call as a bare surface frequency, where the value of 0 is that the soil is always covered, or no bare soil, no bare surface detected, or 1, that means that the soil is always under bare condition, it's always been cultivated. So here we have a picture of the bare surface frequency. That means that the color, the red and yellow, means that the area is always being cultivated, or for example the pink color or the red color indicates that the soil 50% of the time is always bare. It's always not covered by vegetation, where the dark color, for example, here in the mountain area, it's always covered. So by the combining the bare soil frequency, how many times the soil is bare, and also the slope, we can calculate the actual erosion risk. So in some of the areas where the soil is has a high slope, but if it's always covered, then the risk would be lower compared with some areas where it will have a bare vegetation. So we'll look at it in more detail. So for example, here in the paddy fields in the west, in this part, in west of Lombok, we can see that some of the paddy fields is always left bare. This part of the paddy field is always cultivated. We always see bare soil. So the higher the risk of erosion, we see that it's always it's much higher in this part of the landscape where the soil is not always being covered by where the soil is always or mostly covered by vegetation. So within the paddy field, we can identify area where there are risks of erosion because the farmer never covered the soil. The soil is always on tillage. It's always being tilled. And so for example, this area also in the sloping area where we can see the soil is always bare, then the risk of erosion is much higher. And so we can do this at quite reasonable at 30-meter resolution. That means that we can look at the area and see how the farmers have managed their soil in most of the time. And some areas that the color red and yellow means that the soil is always being exposed or bare. That means that there's a high risk of erosion. So the red color means that the soil has a high risk of erosion compared with areas that are green. That means that is less erosion. So that's one example where we take satellite images and we can make a machine learning model to tell us about the risk of erosion and how the soil is being cultivated. Another example I want to show is that we can use the model to actually generate real-time soil moisture about the moisture condition of the soil. So I'm going to take you to Tasmania. Tasmania is in the southern part of the mainland of the Australia. It's not in the mainland, it's a separate island on the south of Australia, where the dots represent a soil moisture observation point station that looks like this. So with a sensor that records soil moisture over time. So these points are discrete points in the landscape. While it can provide moisture content at that particular location, we don't know what is the moisture content throughout at the other places. So what we want to do is we want to make a map, a model which can predict the moisture content throughout Tasmania, but we can see that the data in Tasmania is relatively a small number of points, which are not enough to make a model. So what we can do is that we borrow a model that is already calibrated in Australia using a much larger number of data. And what we do is a model called a transfer learning model. So the Australian model has about 50,000 points. So we first make this model that is calibrated using Australian data. And then we transfer that model into Tasmania, which only has a small number of data points. So here we have the global model or the Australian model, and then we slice the model into different layers. So the new model is that the first 3 layers of the Australian data is kept the same based on the Australian data, but the last layer is calibrated using the Tasmanian data, and we can use it to make a prediction of the soil moisture. So what we show is that if we just use the local model that is calibrated in Tasmania, the performance is not as good as if we use the Australia transferred model. That means the models created in Australia, but calibrated locally in Tasmania. So by doing that, we can have a map of soil moisture that shows how much water is in the soil. That is varying through different seasons from a surface to subsurface layer. And it's also available live. That means every day the farmers can log in and see the condition of not just about the rainfall, but about the water content of the soil. So these are the link that you can use to see how from the machine learning model, from the artificial intelligence model, we can make a prediction of the soil moisture throughout throughout the region and its life every day. And next, I want to talk about the application of artificial intelligence in soil science. So you may think it's some kind of robot, but it's actually how we use the mathematical models. So artificial intelligence is a broader discipline than machine learning. Machine learning is about learning the pattern from the data, but artificial intelligence is about the use of the models to create intelligent design. And this is some part of it is due to the statistics. So the AI is a science of engineering that make intelligent machines using intelligent computer programs. So how can we make this for soil science, the intelligent programs? In order to make the intelligent decisions, it has to have knowledge. And what knowledge can we use in soil science? We can use the pedotransfer functions, which I explained to you before, that, for example, we have calibrated many functions that predict soil properties from other soil properties. And we use it as a knowledge base that makes makes an AI that we can make inference about soil properties from other soil properties. So how does it work? For example, we have the infrared sensors that takes measurement of the spectra of the soil, and we have calibration of the, for example, organic carbon or clay content of that particular soil. But every soil properties, we need some calibration, but we can go beyond that. That means that from that properties, clay and organic carbon, we can also make an inference about other properties because we have these pedotransfer functions that links clay content and organic carbon content to other properties like water holding capacity and so on. So starting from some properties, we can make another other different properties, and then we can make a combination using the uncertainty and so on. So for example, in this case, from the soil spectra, we can make a prediction, not just a clay content and carbon content, but also, for example, other properties. So, for example, the shrinkage of the soil, the organic matter of the soil, the water content, the pH, the water holding capacity, the bulk density, and so on. And finally, I will talk about the use of AI and what's the danger of using AI in the soil science in this particular. So the danger is not that we'll have a robot that's going to destroy the crops, but we will have different kinds of models that we don't know how it's working. So some of it is a proprietary. That means that it comes with an instrument. The instrument said that it can make a prediction of soil pH or nutrient content, but we don't know anything. What's the model behind those instruments? So that is the danger, that we trust the proprietary instrument or prediction that we never have an idea about how it is calibrated, which soil is being used for calibration, and so on. So we should not use those kind of models that we cannot interpret, or we don't know how the data were generated for. And also, there's a danger that we use the machine learning to treat soil as a soil materials without any knowledge about what type of soil or what kind of soil properties it can use. And by doing that, we lack of a new theory because we dependent heavily on the machine learning, so that we never create a new theory, and we try to do too much with too little data. If we have too little data, then sometimes we use machine learning, and we think that we can make a generic prediction, which is not necessarily true. And finally, if we rely too much on the machine learning, then there will be not enough human field observation or field work to validate the actual prediction that we use. Okay. As a summary, that for this presentation is that the combination of machine learning and soil science domain needs to be developed together, so it's not one or the other, so that it can be a more meaningful models. And we also need to do model interpretability. That means that we need to understand how the model is calibrated and why it works. But we also need to know the underlying physical and chemical properties. And that's why we need to incorporate soil knowledge into modeling processes, so we can have a better understanding about the soil properties and processes that can lead to better informed interpretation of the model's predictions. Thank you very much for your time. I think I stop here.
Thank you very much, Professor Budiman. So next we move to the discussion session. Maybe we start the first session by 2 or 3 questions.
Thank you very much. I would like to respond the last presentation. It's really interesting talking about the machine learning. Hello, Professor Budiman. Can you hear my? Yeah. I'm Sukartono from Department of Soil Science, University of Mataram. I met you last time in Lombok. So it's really interesting to hear about the use of machine learning in soil science. So from your presentations, it's a bit far from the here condition in Lombok. Do we need the complete database on soils to fulfill the what we call to fulfill the how machine learning can work? That's the first question. The second questions here in Lombok, we determine fertilizer recommendation for several food crops. Mostly we use conventional method using field experiment and soil analysis. But now, Professor Bambang already buy a sort of sophisticated tools we call infrared. And from this tool, I think we can use to make it simple how to prepare recommendations. But until now, still under what we call prepare for soil survey with the several staff from University of Mataram. Maybe we already discussed about that, and some lecture already takes soil samples and analyze some soil properties, and in several agroclimate in Lombok, rain-fed, irrigated area, etc. So do we need a sort of several calibration in each of agroclimate, Professor Budiman? Hello?
Hello. Yes.
Okay.
So I can answer straight away.
Yes, please answer.
Thank you, Mr. Moderator. Thank you for your questions. So for the first question is that you ask if you need a complete coverage of the soil data. Of course you do, because the machine learning model can only learn what is given. So the map that I show about the Lombok is based on a limited number of samples. Although I can make the map of the full island of Lombok, but I know that there's a limitation because the data or the prediction is only valid in the areas where we have collected the samples, and there are still many areas that are not fully covered by the samples. So indeed that we need, the more data we have, then the models are more accurate to capture the information. And the second question is about the fertilizer recommendation. I think because you mentioned you have many traditional experiments. I think one of the way that machine learning can help is that we take all the data from the traditional experiments and we can make a model to show us at different locations how the nutrient is affecting the crop yield or crop production. And for your models of infrared, you are correct that I think it should be better to group the soils based on different agroclimatic zones. I think that will be more representative, that will be more accurate for the local application. Thank you.
Okay, we can discuss later, Prof. Budiman, after the staff from soil science collecting data and do some measurements in the lab. See you next time.
See you. Thank you.
Okay, thank you very much, Prof. Skartono and Professor Budiman for the answer. So next question.
Okay, thank you for the opportunity. My name is Joko. I would like to ask to Prof. Budiman. Thank you for the interesting presentation. The first question is how you transfer the general model of Australia to specific area in Tasmanian model. How to do that? I mean, like general model, and then you transfer to a very local model. And the second one about the landslide risk for Lombok, I think. Is that first? Have you published it so we can read more detail about it? And the second one, did you need also land cover type to predict whether this location has high risk or low risk? Okay, that's my question. Thank you for the answer.
Maybe you can also answer directly, Prof. Budiman.
Thank you. Thank you for the question. So the first question is that about the transfer learning. So in neural networks, the model is made up of different layers. So different layers. So maybe I can share my slides again. That the machine learning model is made up of different layers. So for example, in this example, I have 4 layers. This is just an example. So this is the Australian model that I can make, that I train all the full model. So it has 4 layers. But for the application to local area, I take the first 3 layers from the Australian model. But the 4th layer, I make it as I make it not fixed, but it can be trained, it can be calibrated using local data. So the first 3 layers are fixed. That is the coefficients are from the Australian model, but the last layer, the model is trained using local data. So at the end, so this is, if I compare this to the global model, the first 3 layers are the same and the last layer are different. So this one is using the Australian data and this one is trained using the local data only on the last layer. So this is what is called transfer learning in a machine learning. And the second question is about the erosion risk, or I don't call it it's not a landslide risk, but erosion risk. So what we do is we are not detecting the land cover type, but we are detecting how often the soil is bare or not covered by vegetation. So because in some areas in Lombok, the farmers always cultivate their soil. They like to keep the soil bare or keep the soil clean without vegetation. But that also makes the soil to have high risk of erosion. So if the area is flat, then the risk is not so high. But most of the time, the area is on the slope, even on some slope. That means that there is a high risk of erosion. So even in the area of a gentle slope, but if the farmer just keep cultivating the soil or till the soil, that means the erosion risk is high. So we don't detect it. It hasn't been published yet. So because Pak Bambang and Pak Arifin wants me to give this presentation, I give it as an extra, about the analysis in Lombok that we can use remote sensing images and also to see something about how the soil is being managed and to calculate the erosion risk. Thank you.
Thank you very much, Professor Budiman. Because limitation of time, maybe just one more question. Is there any question?
Yeah, thank you for this very technical, wonderful presentation. I wonder if ML is already used integrating AI so that there is maybe a better connection between this capture of data and theory that are underlining your field.
Sorry, so this question dedicated to Professor Budiman. Oh, yes. So, Professor Budiman, please answer.
Okay, thanks for the question. Yes, you are correct that at the moment, the machine learning is still not integrated into the AI yet. So that's why at the last part of my presentation, I proposed that because machine learning, you can make prediction of various soil information. These machine learning models become a knowledge base. And the next step we need to do is that we need to implement the AI stage that where there's some intelligence of using the machine learning models prediction. There is some decision making that takes the predictions into some meaningful predictions about characterizing the soil. Thank you.
Thank you very much for all the answer and question for this first plenary session. So we close this morning first plenary session for today. Again, please give applause to the all of three keynote speakers. Okay, that's all from this first session. Thank you very much for all participants, and I give back to the MC.
We would like to say thank you to all of our three keynote speakers and to our outstanding moderator today, to Dr. Igede Putu Weda Swarawirawan. Please give a big round of applause for him. Ladies and gentlemen, we're going to the next agenda. We will give a certificate to our keynote speakers today. We would like to invite Professor Dr. Insinyur Adi Susilo, MSc PhD, to come to the front of the stage, and would like to ask Professor Sukartono to give the certificate to Professor Dr. Insinyur Adi Susilo. Thank you so much. Please give a big round of applause. Ladies and gentlemen, here is the end of our first plenary session. We're going to take a break until 1 p.m. So we will meet you guys at 1 p.m. sharp here in the ballroom for our second plenary session. Please have a break and we'll meet at 1 p.m. today, 1 sharp in this ballroom. Thank you once again to our moderator and keynote speakers today. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Bapak Ibu yang kami hormati, waktu break adalah dari pukul 12.23 hingga pukul 13.00 siang nanti. Kita akan lunch di Kunyit Restoran, first floor, not first floor, tapi di lobby, ground floor. Kita akan lunch di lobby di Kunyit Restoran. Jadi setelah keluar dari lift, Bapak Ibu belok kiri, you can turn left and then you can have your lunch at Kunyit Restoran. We are going to have a second plenary session at 1 p.m. sharp. Thank you.